Distance learning curricula in machine learning, classification and its applications. Good afternoon and welcome to the machine learning course. This course was developed as a result of the Erasmus Plus project Code-In. All you need to learn is internet access and a computer. The course contains a total of 10 topics, and in this topic, we will say something more about the classification and its applications. Classification is a type of supervised learning where the goal is to predict the class label or category of a data point based on a set of features or independent variables. In this type of learning, the data is labeled, meaning that each data point is assigned a definite class label. Classification is used in many real-world applications, such as sentiment analysis, spam filtering, image classification, and medical diagnosis, among others. The success of the classification depends on the quality of the training data and the choice of algorithm used. There are many different classification algorithms to choose from, ranging from simple linear models to complex ensemble methods. For beginners, it is often best to start with simple and widely used algorithms, such as logistic regression, decision trees, k-nearest neighbors, and naive Bayes. These algorithms are relatively easy to understand and implement, making them ideal for getting started with classification problems. They have been widely tested and used in various domains and have shown good performance for many problems. Logistic regression is a statistical method used for binary classification problems, where the goal is to predict a binary outcome, for example, yes, no, true, false. It helps to determine the relationship between a set of independent variables and a binary dependent variable. The independent variables are used to predict a probability of the dependent variable being either 0 or 1. This probability is then transformed into a binary outcome using a threshold value, usually set at 0.5. If the probability is greater than 0.5, the outcome is predicted as 1, yes, true. And if it's less than 0.5, the outcome is predicted as 0, no, false. The logistic regression model is trained on a labeled dataset to learn the relationship between the independent variables and the dependent variable. During the training phase, the model learns the coefficients for each independent variable, which are used to calculate the probability of the dependent variable being 1 or 0. In summary, logistic regression is a simple yet powerful method for binary classification problems and is widely used in many real-world applications, such as predicting customer churn, loan default, and disease diagnosis. Let's say we have a data set of 100 customers, and we want to predict whether or not they will buy a certain product based on their salary. We can use salary as the independent variable to predict whether or not a customer will buy the product. The logistic regression model will learn the coefficient for salary, which will be used to calculate the probability of a customer buying the product. In this example, the x-axis represents the salary of the customer and the y-axis represents the probability of a customer buying the product. The curve shows how the probability of a customer buying the product changes as the salary increases. At low salaries, the probability of a customer buying the product is low, but as the salary increases, the probability also increases. At a certain point, the probability levels off and approaches 1 as the salary continues to increase. The curve follows an S-shaped pattern, which is typical for logistic regression curves. This logistic regression curve was created based on the coefficients learned by the logistic regression model. The actual coefficients and shape of the curve may be different in the real data set, but the general pattern of the curve will remain the same. showing the relationship between the independent variable, salary, and the dependent variable, bought product. Here is a high-level overview of the steps involved in the learning process of logistic regression. The learning process in logistic regression involves finding the best parameters, weights that can be used to make accurate predictions. The algorithm starts with an initial guess of these parameters and then iteratively adjusts them based on the training data. K-nearest neighbors, KNN, is a simple machine learning algorithm that is used for classification and regression problems. In KNN, a new data point is assigned a class or a value based on its K nearest neighbors in the training dataset. KNN is a simple and effective algorithm that can be used for a variety of problems, but it does have some limitations. For example, it can be computationally expensive when the training dataset is large, and it can be sensitive to the choice of K. Despite these limitations, KNN is a good algorithm to start with for many problems, especially for small datasets or when you need a quick solution. Imagine you're in a room filled with triangles and squares, and you've just met a new shape. You're not sure if it's a triangle or a square. KNN is a machine learning algorithm that helps you find the closest shapes in your data. First, you have to choose the number of nearest neighbors K. In this example, for the dashed line circle, the value of K is 3, and for the solid line circle, the value of K is 5. Next, we'll measure the distance between the new shape and all the other shapes in the dataset. If the number of nearest neighbors is set to 3, represented by the dashed line circle, the new shape will be classified as a blue square. This is because within the inner circle, there are 2 blue squares and only 1 red triangle. However, if the number of nearest neighbors is set to 5, represented by the dashed line circle, the new shape will be classified as a red triangle. This is because within the outer circle, there are 3 red triangles and 2 blue squares. Naive Bayes is a way of categorizing things, like people, documents, etc., based on their characteristics. It's based on a simple mathematical formula and makes assumptions about how the characteristics are related to the category. To use naive Bayes, you need to know what groups you want to make and what qualities each item has. Then, the algorithm looks at a bunch of items that are already labeled and uses that information to figure out how to categorize new items. In short, naive Bayes takes things you know about, learns how to group them, and uses that knowledge to categorize new things you don't know about yet. Here are the steps for implementing the naive Bayes algorithm. Define the classes. The first step is to define the classes that you want to classify your data into. For example, if you're trying to classify fruits, the classes could be apple, banana, orange, etc. Define the features. Next, you'll need to define the features that you'll use to make your predictions. For example, in our fruit classification example, the features could be the color, size, and shape of the fruit. Count the number of occurrences of each feature in each class. For each class, count the number of occurrences of each feature. For example, count the number of red apples, yellow bananas, etc. Calculate the prior probabilities. The prior probabilities are calculated based on the number of instances of each class in the training dataset. For example, the prior probability of apple is the number of apples in the dataset divided by the total number of fruits in the dataset. Calculate the likelihoods. The likelihoods are calculated based on the number of occurrences of each feature in each class. For example, the likelihood of red given apple is the number of red apples divided by the total number of apples in the dataset. Calculate the posteriors. The posteriors are calculated by multiplying the prior probabilities and the likelihoods. For example, the posterior of apple given red is the product of the prior probability of apple and the likelihood of red given apple. Choose the maximum posterior. The last step is to choose the class with the maximum posterior as the predicted class for a new item. In other words, the class with the highest probability of being the correct class is chosen as the prediction. Let's put it all together. You have a basket with 20 pieces of fruit, 10 of which are apples and 10 of which are oranges. The apples are divided into two colors, red, 6 apples, and green, 4 apples. The apples also come in two textures, smooth, 8 apples, and rough, 2 apples. The oranges come in two textures, smooth, 2 oranges, and rough, 8 oranges, and also come in two colors, red, 2 oranges, and orange, 8 oranges. Now, you have a new piece of fruit and you want to determine if it's an apple or an orange. The fruit is red and has a smooth texture. Here are the steps to calculate the prior probabilities, likelihoods, and posteriors for this scenario. The prior probabilities are the initial probabilities of the fruit being an apple or an orange before considering any other new information. The prior probability of being an apple is 0.5. The prior probability of being orange is 0.5. The likelihoods are the probabilities of the fruit having a red color and smooth texture, given that it's an apple or an orange. The likelihoods of being an apple and having a red color is 0.6. The likelihood of being an apple and having a smooth texture is 0.8. The likelihood of being an orange and having a red color is 0.2. The likelihood of being an orange and having a smooth texture is 0.2. The posterior probabilities are calculated by dividing the joint probabilities by the denominator. By doing this, we get the probability that the fruit is either an apple or an orange, given the new information that it has a red color and a smooth texture. The first part of the expression, 0.5 multiplies 0.6 multiplies 0.8, represents the joint probability of the fruit being an apple, having a red color and a smooth texture. The second part of the expression, 0.5 multiplies 0.2 multiplies 0.2, represents the joint probability that the fruit is an orange, red color, and has a smooth texture. By adding the two joint probabilities, we get the denominator of the posterior probabilities, representing the total probability of the fruit having a red color and a smooth texture. After considering the new information, the posteriors are the final probabilities of the fruit being an apple or an orange. The posterior probability of being a red and smooth apple is 0.952. The posterior probability of being a red and smooth orange is 0.048. Therefore, the new piece of fruit is likely an apple, with a probability of 0.952 or 95.2%. Here's an example of a decision tree for the Titanic passenger survival data, designed for a beginner. It is fairly easy to interpret data from a decision tree. This is one of their strengths. It's important to keep in mind that this decision tree is still a simplified representation of the complex interactions between various factors that contributed to passenger survival on the Titanic. Additionally, this decision tree only considers 3 variables, age, gender, and passenger class, and does not account for each other factors such as ticket price and location on the ship that could also have had an impact on passenger survival. In essence, a decision tree is a simple and intuitive way to make predictions by breaking down a problem into smaller and smaller questions until a final answer is reached. The goal of building a decision tree is to create a model that accurately splits the data based on the features and makes accurate predictions. In the Oracle Academy materials that are part of this course, you can find and use more detailed examples of using the ID3 algorithm. The ID3 algorithm starts with a single node that represents the entire dataset and recursively splits the dataset into subsets based on the values of the selected attribute until all instances in a subset belong to the same class or until a stopping criterion is met. At each node, the algorithm selects the attribute that has the highest information gain and creates a branch for each possible value of the attribute. The algorithm continues until it has created a decision tree that fully classifies the training data. While the ID3 algorithm is a popular and widely used decision tree construction algorithm, it has some limitations, such as its tendency to overfit to noisy data and its inability to handle continuous valued attributes. Several variations and extensions of the ID3 algorithm, such as C4.5 and CARD, have been developed to address these limitations and improve the accuracy and robustness of decision trees. To complete this unit, study and review the following online resources. Thank you for attention.